In this video, we're going to talk about organic chemistry. So first of all, what is organic chemistry? Organic chemistry is the study of organic compounds. Now, the question becomes, what are organic compounds? Organic compounds are going to be things like sugars, oils, fossil fuels, alcohols. You could even say benzene. But the main point is that they are carbon compounds. Now, inorganic compounds are generally going to be ionic compounds that contain metals. So, in here, magnesium is the metal. Also, water would be an inorganic compound because it doesn't have carbon, but also carbon dioxide would be an inorganic compound. Now, how is carbon dioxide an inorganic compound if it has carbon? Well, generally speaking, organic compounds have carbon and hydrogen together, bonded. So that's the important thing about organic chemistry. And there are some exceptions. So, for example, if you have tetrachloromethane, this is organic, but it doesn't have any hydrogens in it. So the carbon-hydrogen bond is very important in organic chemistry. There are a few exceptions like this one, but they're pretty rare. Now, some other elements which are going to be in organic chemistry other than carbon and hydrogen are going to be things like boron might be in there, nitrogen, oxygen, the halogens. You're going to have sulfur, probably silicon, and maybe even phosphorus. Now, boron is going to be pretty rare, so maybe we don't include boron. And also keep in mind all of the macromolecules are going to be organic compounds, so proteins, carbohydrates, and fats or lipids. Now, we said that, generally speaking, organic compounds are going to contain carbon bonded to hydrogen. Now, if a compound has only carbon and hydrogen, it is going to be called a hydrocarbon. So let's go through a few examples of hydrocarbons. Let's go through the elements that we talked about. So we had hydrogen, carbon, nitrogen, oxygen, the halogens, and we also had sulfur, phosphorus, and silicon. How many bonds do each of these elements make? Hydrogen usually makes 1. Carbon and silicon make 4. Nitrogen and phosphorus make 3. Oxygen and sulfur usually make 2 in their neutral states. And the halogens make 1. Now, if you forget this, but you have a periodic table, a quick way to find that out for elements that are on this side, hydrogen is going to be an exception, is that these are going to have groups. So carbon and silicon are going to be group 4A, and then nitrogen and phosphorus 5A, 6A for the chalcogens and then 7A for the halogens. If you take the number 8 and then subtract it by the group number, so if you have 4A, you put 4, you get the number of bonds that it would make. So valence electrons, or actually, sorry, just number 8 minus the group number, which is equal to the number of valence electrons that the atom has, or the element has in its neutral state. And that should give you the number of bonds if the element is neutral in most cases. The reason this is the case is because these elements want 8 electrons in their valence shell, and so each bond that they make adds 1 electron to their valence shell. And so since they want to all get to 8, they need the correct number of bonds to get there. So now let's take the structure CH4. This would be a condensed structure. You could also call it a molecular structure. The difference, so now let's take the structure CH4. This would be a condensed structure. You could also call it a molecular structure. The difference, so now let's take the structure CH4. This would be a condensed structure. You could also call it a molecular structure. The difference, so now let's take the molecular formula of C2H6. This is the molecular formula. How would you draw the Lewis structure of C2H6? So you know that you have 2 carbons and that you have 6 hydrogens. You know that hydrogen forms 1 bond and carbon forms 4. So you try to arrange them to make it so that carbon has 4 and hydrogen has 1. So it would look like this. Another way to approach it, which I sort of did, is to draw the number of carbons. Just draw the carbons next to one another, and then distribute the hydrogens equally among the hydrogens. So if you have 2 carbons and you have 6 hydrogens, each carbon would get 3 hydrogens. So you'd put 3 around each, and then you would connect the hydrogens with the carbon with 1 bond, since hydrogen forms 1 bond, and then you'd figure out how many bonds you need in the middle. So now carbon likes to form 4, so this one has 1, 2, 3, and needs 1 more, and this one has 1, 2, 3, so it also needs 1 more. So 1 bond here would fulfill the valence shell of all of the atoms in this structure. So now, before erasing it, how do we draw the condensed structure for this? You can write CH3, CH3, because you have a CH3 here and you have a CH3 here. We went over what C2H6 looks like, so now let's go over what C2H4 would look like. So you have your 2 carbons and you have 2 hydrogens per carbon. So you'd put 2 hydrogen next to each carbon and then you would connect them. In this situation, each carbon has 2 bonds, so it needs 2 more to get to 4. So how would we bond these 2 carbons together? So in organic chemistry and in covalent bonds in general, what you can do is have a double bond. Each bond represents 2 electrons that the atoms are sharing. If you have a double bond, like we do here, that would mean that it's sharing 2 and then it's sharing 2 more. The other two look kind of like that, but we just draw it as another line. Now let's go through another example. Let's say we have C2H2. What do we do in this situation? We have our 2 carbons, and we have a hydrogen for each carbon. What sort of bond would we need in the middle? This time we're going to need a triple bond. Now, a triple bond is the max number of bonds that can be created between 2 atoms in covalent bonding. I've gone ahead and redrawn the 3 structures that we had just to make it clearer. So now, what do you notice about these 3 structures? What is similar about them? The only elements that they contain are carbon and hydrogen. When a compound has only carbon and hydrogen, it is called a hydrocarbon. So these are all hydrocarbons. Now, there are different types of hydrocarbons. The one on the left only has single bonds. The bonds between the carbons are only single. Therefore, the number of hydrogens is the maximum that it can be given the number of carbons. So therefore, we call them saturated hydrocarbons because they have the maximum number of hydrogens, and so they are saturated with hydrogens. These 2 on the right, they are called unsaturated hydrocarbons because they have either double or triple bonds in between the carbons at least once, and that makes it so that you cannot have the max number of hydrogens because this one has 6 hydrogens, but this has 4 and this has 2. Also, these types of hydrocarbons have their own names. So the one on the left, when you have only single bonds between the hydrocarbons or between the carbons, it is called an alkane. The one in the middle, when you have at least one double bond, is called an alkene, and the one on the right is called an alkyne. So now let's go over the names of some of these bonds. I've referred to this as a single bond, and I've called this a double bond, and I've called this one a triple bond. But these actually have specific names for the bonds. Now, I'm going to redraw these with different colors so that you can understand what I mean. If 2 atoms form one bond between each other, one covalent bond, this bond is referred to as a sigma bond. If they form more than one bond, the first bond that forms is going to be the sigma, and then the ones that come after is going to be called a pi bond. So, in a double bond, there is one sigma bond and there's one pi bond. In a triple bond, there is one sigma bond and there are 2 pi bonds. Now, out of these 3 situations, which one of these bonds is stronger? The one on the right is stronger because 3 bonds are stronger than one or 2 bonds. However, let's take another comparison. Which one of these two is stronger, a sigma bond or a pi bond? The answer is a sigma bond. Even though two pi bonds in a sigma bond is stronger than one sigma bond, a single sigma bond is stronger than a pi bond. Now let's compare something else. Which one of these bonds out of the three is going to be the longest, and which one is going to be the shortest? The answer is going to be that the one on the left, the one that has one sigma bond, is going to be the longest, and the one on the right with three bonds, one sigma bond, two pi bonds, is going to be the shortest. So that's an overview of these hydrocarbons. Now let's say you're given the number of carbons that each of these types of hydrocarbons have. How do you figure out the number of hydrogens that they're going to have? So for alkanes, the general rule is this. N is the number of carbons that we have in the compound. So let's say we have 6. You'd plug in the same number here for N on the hydrogen side. So 2 times 6 plus 2. 2 plus 6 is 12, and plus 2 is 14. So if you have an alkane with 6 carbons, you're going to have 14 hydrogens. For alkenes, it's going to be double the number of hydrogens per carbon. So if you have 6 of them, it'd be 2 times 6, which is 12. For alkynes, it's going to be 2n minus 2. So if you take the number of carbons that you have, you multiply it by 2 and subtract it by 2. Now, how about naming them? If you have CH4, and if there's no number in front of the C, it means it's a 1. This is called methane. If you have C2H6, it is called ethane. If you have C3H8, this is called propane. C4H10, this is called butane. You probably want to memorize these. C5H12 is pentane. C6H14 is hexane. And C6H16 is going to be heptane. Actually, that was wrong. Sorry. It's going to be C7. C8H18 is decane. C9H20 is nonane or nonane. Once again, another mistake. So this is actually octane. And then C10H22 is decane. Now, if you were to do this for alkanes, you would just change the ending. So for alkanes, you had ANES, or ANE as the ending for all of them, right? But if you were to do it for alkenes or alkynes, you would just change the ending. So an alkene, you can't really have an alkene with one carbon because it wouldn't be able to double bond to another carbon, so you'd start with the second one. So I'm not going to do the formulas because you can figure them out using this equation, but for alkenes it would be ethene, propene, butene, pentene, hexene, heptene, octene, nonene, and decene. And for alkynes, you would have ethyne, propyne, butyne, pentyne, hexyne, heptyne, octyne, nonine, and then decyne. So the first 10 for these you generally want to memorize for organic chemistry. So now let's say you don't have only carbon and hydrogen. Let's say you have other elements like oxygen, nitrogen, phosphorus, the halogens, or other stuff. So in this particular situation, we're going to draw the Lewis structure for a 4-carbon compound that has an OH at the end of it. So usually start drawing all the carbons, and then you would draw the hydrogens, and then at the end you have an OH. Now in this particular situation, every time you have an OH, it is going to be an alcohol. This is an alcohol functional group. This particular piece is called a hydroxyl. So every time you have a hydroxyl group, it's going to be an alcohol. Now, how do we name alcohols? If you remember, we had things like meth, and then we'd have the suffix ane if it was an alkane. You'd have ene if it was an alkene, or yne if it was an alkyne. In this case, we're going to use the suffix a-N-O-L. So this would be called, so if you have a alcohol with one carbon, it would be called methanol. And in this particular situation, we have a alcohol with 4 carbons. Let's see how many hydrogens we have. That should be 9. We're going to have butane was the prefix, and then the suffix is going to be a-N-O-L. So this is called butanol. Now there are a lot of things I didn't go over in this video because this is just an introduction to organic chemistry. So for example, in organic chemistry at the beginning you're going to have to do something called nomenclature, where you name all of these compounds. I went over a little bit of that, but there's a lot more to it. Also, there are a lot of more function groups. So for example, this would be, I don't know why my pen is bugging out, but let me just, yeah. So for example, this would be an aldehyde functional group. One moment, guys. My pen is just... This would be a ketone. This would be a carboxylic acid. And then R is just anything, like it could be literally anything. This would be an amine. But if you search up our channel and go on the videos, you should see videos about a lot of other subjects for organic chemistry. But for an introduction, that should be enough. So I hope you enjoyed that video. Leave any questions you have in the comments. Thank you for watching.